Okay, I'd like to start with a little experiment. I am a scientist after all. So soon, the technical staff on site should be able to play a video for you in the audience. But before they start, I would like, if you may indulge me, if everyone in the audience could raise one hand. I can't see if you do this or not, but please raise one hand. And this hand means that you are waiting to cross a street. I think you probably see a street on the screen right now with some cars. And soon these cars will start moving. And I'll ask you to please take your hand down when you feel that you would be safe to cross this street. So taking the hand down means crossing the street, okay? Hands in the air. Okay, technical staff, please play video 1 now. Okay, perfect. I think that seems like that worked. We're going to do it once more. Almost the same thing, slightly different video. So please, hands in the air one more time. And when you have your hands in there, I'll ask the technical staff to please play video number 2. Now, please, yeah, if you aren't already. Perfect. Thank you very much for that. I don't know how it was for you. I think you can now see my screen again with a couple of diagrams here showing how participants in our experiments in Leeds when we do this type of scenario typically respond. So in the first scenario, the first video, you might have sensed a bit of sort of uncertainty what was happening. Was the car stopping for you or not? And it might have taken you a bit longer in the first scenario, as you see on these graphs, than in the second scenario, where you probably felt more certain and more quickly about what was happening. So this is just one example of how quite subtle little signals in what we do can make quite a bit of a difference. So what you might have noticed or not was that in the first case, the car just stopped exactly where you were, whereas in the second case, the car was signaling its yielding a bit more clearly with a bit more deceleration. So yeah, subtleties of how humans interact on roads. Then if you think about automated vehicles, today's deployments of automated vehicles typically happen mainly in this kind of environment, right? These highway environments where there is almost no interaction with other human road users. The sort of state-of-the-art deployments at the moment, various trials, experiments ongoing are in this kind of environment, right? The US urban environment where there starts to be more interaction with humans, certainly, but they are still relatively few and they are pretty scripted and there are a lot of rules and traffic lights and so on. We still haven't completely solved this kind of challenge, but this is sort of where we're at the moment. And if you look at the rest of the world, parts of Europe, Asia, Africa, and so on, it looks more like this, right? Where you basically won't get anywhere unless you have figured out how to interact with human road users, right? So arguably, if you want to make and sell automated vehicles, the further to the right you can get in this picture, the better it's going to be, right? But the flip side is also that if you try to put an automated vehicle too far to the right in this picture when it's not ready for it, you might face quite substantial problems with human acceptance of your automated vehicle. So take just this simple situation as an example. You're an automated vehicle driving on the street and you see this couple walking a bit weirdly on the street itself. And as an automated vehicle, even though these guys, they're not planning to pass anytime soon. They know you have the right of way, but you become uncertain as an automated vehicle. You start slowing down a little bit to be safe. And these guys pick up on that. And as we saw in the first videos, they might decide that, yeah, actually this car is stopping for me. So we go ahead and cross. And that's all very nice with respect to the pedestrians, but the surrounding car drivers might be quite frustrated with you because you're not doing what's expected of you. And for sure, automated vehicles raise quite sort of strong emotions in humans. It's not only about how they drive, it's about other things as well. But I would argue that certainly as a sort of minimum level, we need to make these cars interact well with human road users if we are ever going to see acceptance, widespread acceptance among human road users of them. So what I would propose is that this sort of upshot of this is that we can't think of automated vehicle making only as an exercise in robot building. It's as much, or possibly even more in some ways, an exercise in human understanding. We need to understand humans. And the scientist's way of saying this is that we need models of human behavior, right? That's one way of expressing understanding. And today we don't really have this. There are no existing ready-made models of how humans behave in traffic. But we do need them. We need them to be able to predict what's going to happen next based on sensor data in real time. We need models there. We also need it for simulated safety testing, right? You might have heard that we're going to ensure that automated vehicles are safe by running billions of miles of testing in simulation. But if there are no good models of human behavior in those simulations, if they're basically just empty of human life, how convincing is that safety testing? Okay, but so how do we do it? If we don't have it, how do we do it? Obviously, it starts with data on how humans behave. And we can collect lots of that. And then the simplest way of creating a model based on that is to just press play on the recording, right? And as you may know, that's done to a large extent by all major players already. Collection of large amounts of actual log data from real traffic, and you replay that. And in some ways, it's a perfect model of human behavior, but only as long as the circumstances where you're testing it. Because what you're doing is you're taking your new software version for your automated vehicle and you're running it through the same log data again to see that it's still working. But if that software upgrade causes a slight change in the behavior in whatever way to the automated vehicle, you don't know any longer that the behavior of the surrounding road users would have been the same, right? So then you need what you'd perhaps more typically call a model, a sort of closed loop model that can respond to the behavior of the automated vehicle. And in this machine learning rich environment, you might think of machine learning methods. We have these behavior data. We can apply deep learning neural networks to these to sort of learn a model of human behavior. And that's a viable approach. I think it's a good approach. And we start seeing some models coming out like that, which sort of, when you look at it, seem to behave sort of like human behavior. It brings to mind a little bit some of the other more well-known AI developments, like recently GPT-3, for example, this natural language AI that can produce very human-like, but not always quite human-like texts. Prompting this tweet by Jocha Bach, GPT-3 has intensified my fear of being governed by, oops, sorry about that, by machines that are always slightly wrong about the most important things, but in so subtle ways that human intellects are usually not good enough to spot the differences. So I think there's a similar concern here, that we can have these machine learned models which look sort of okay, but do they really capture the important bits, these subtle interactions that are important to humans? Do they generalize well to safety critical situations that are going to be very scarce in any behavior data set? So my argument is that we need those models, but we also need to complement them with some good old-fashioned scientific understanding in terms of models that aren't black box in nature, but that are instead based on what we know from psychology and cognitive neuroscience about humans. So that's the kind of model we're working on in my team primarily, making these little types of people that can exist in simulations, for example, such that if there's something wrong with the automated vehicles, it's these guys who suffer, not an actual human. And what we can do then is that we can actually start understanding what we see in our experiments and on real roads. We can make models that reproduce the human behavior, and we can understand that they do so because they're using the same kinds of perceptual and sensory information as humans use. And they're processing that information with the same types of decision-making mechanisms that humans use. And then we can close the loop, so to speak, and put this into simulations. You're going to see soon a couple of animations at the same time. So you need to use both your eyes. To the left, you're going to see 50 simulations on top of each other with a car that decelerates in this way that you saw first, just to precisely stop at the pedestrian crossing. And to the right, you're seeing a car that's stopping a little bit more obviously. So if you're not playing the video already, could you go ahead and play it now, please? Video 3. So you'll see that Pedestrians in the left-hand simulation, they tend to get stuck, quite a few of them, because they're not quite understanding what the car is doing, which means that the car has to come to a full stop before it can proceed, which means that it ends up losing quite a bit more time. So actually, this kind of behavior, which is nice towards the pedestrian in terms of being clear, is also good for the automated vehicle itself. So you can stop that video now, please, if you haven't already. Okay, so that's the point. So that's just one sort of simple example, but I think it drives home my main point, which is that to make good self-driving cars, we need a substantially improved understanding of human behavior. Thank you very much.